review. So they have 5 minutes.
Yes. 那我这边现在
现在没有在干嘛？
毕竟他们现在也很不会说这个来这种怪号怪症状就是我来这个。哎，谢谢谢谢。所以你们是刚刚才知道这个状况。
我们原本有这种状况，
原本知道说他们在那里已经被锁起来，但是
可是他锁起来是马上是 reporter， 他要在当 reporter 被锁。那件事是系统的问题。
我们刚刚也是他们打碰的时候还是被锁，所以刚还走这个方法。
对。
然后因为我有注意到规则里面有3次，所以刚才还是
对，因为那个是系统，因为那个是系统的 bug， 因为全部的角色只有1个人打3次，所以一个人最多上场次数可以到13次，就是553这样，这是系统允许的最上限。对，但是目前看起来那个系统当初在写的时候，可能这个 bug 没注意到，所以这个开始。
然后刚刚我是大概3分50秒钟开始，然后加3分钟就是到6分50，6分50。
再去跟他讲一下，他说可以跑到6分50，那免得他一直很紧张要往上上。谢谢。因为我觉得就是学生难免会遇到，如果没有事先提醒他。他们就会记得。OK，
好，谢谢老师。
And today I'm going to talk about the three-sided dice. And here's our outline of my presentation. First of all, we're going to talk about the problem statement and probably focus on and the observation video that we did and the simple theory. Then we're going to the experiment part, and we will modify our theory again and do another experiment. And in the end, we're going to have a conclusion and claim. And here's the problem statement. To land a coin on its side is often associated with an idea of a rare occurrence. What should be the physical and geometrical characteristic of a cylindrical dice so that it has the same probability to land on its side or one of its faces? So the main focus point of my team is analyzing the physical and geometrical characteristics. So this too is both very important in this problem statement and same probabilities in the three-sided dice of its faces and the side. And we're going to focus on the existence of the three-sided dice in the reality. And here's our observation video. And here's the video that we throw the dice by our hand, and we can see that this is a basic motion of the dice that we throw the dice, and it's very complicated because it has the bounce and the rotate and something else like the video shows. So here's our simple theory about the geometric characteristic and the center of mass. And first of all, we're going to talk about the center of mass. And in this object is same as our dice, like in this way, and this is our object. And because it's uniform, so the center of the mass, also called the center of gravity, is in the middle of the object, like the yellow, orange dot shows that the side of the cylindrical dice, and here's the center of the mass. So we will calculate the mass from this part, this dot. Okay, and here is our theory, and we're going to talk about in the geometrical characteristic. It will fall like this way or fall like this way. Okay, so when the theta that we define, theta is like here is the theta, and theta is lower than f tangent 2 radius divided the height, and it will go the head and the bottom, like the picture shows. And when theta is greater than f tangent 2 times radius divided the height, and it will come to fall on the side, like the picture shows. So here's our calculation of the probability of falling on the top, the bottom, and the side. And here is our ideal condition of the dice. And this is our three-sided dice, and the equal probability will like this. And after our calculation, we can know that the ideal three-sided dice is 2 times radius divided height is about √3. And this is our ideal three-sided dice that will have the same probability of falling on the head, the bottom, and the side. And let's talk about our first experiment. And this is our experimental setup, and it's the same as this kind of dice. And we have 3 kinds of the dice by having different ratio of the diameter and the height. And here have the diameter divided by height is 1, and √3, and 2. And here's our experimental design of our first experiment. And first, we use 3D printer to print the cylinder with a given proportion of diameter and height, like this one. This is using the 3D printer to print out. And we mark the dice from 1 to 3 area. And this is the first area, and the side is called the second area, and this is the third area at the bottom. And we roll the dice for about 1,500 times for each kind of dice. So we have 3 kind of dice, and we just roll them, each of them about 1,500 to 1,500 times, and we will calculate the result. And here is our experimental data. And this is the 3 dice that we rolled. And we can find that the chance of falling on the bottom, the top, and the side is like this. And in the ideal, the probability of falling on the bottom, the top, and side, in this dice it will be 1 to 1 to 1. But in our experimental result, it seems not like 1 to 1 to 1. And we're going to find out why is the geometrical characteristic that we calculate is not fit our theory. And so we did some comparison about this experiment. The experimental data doesn't fit our theory well, as you've seen before, and we make an improvement and also modification. And here's the theory that we modified. And we adding the physical characteristic and the initial conditions in this experiment. And here's the physical characteristic in the initial condition that we could have considered about, like the angular velocity, the linear velocity, the position that drop the dice, and the normal vector, the gravity, and the coefficient, or like the friction or something, is so on. It's pretty much physical characteristic. And here, let's talk about the ideal condition. What is an ideal condition? We believe that if we can control all the physical and geometrical characteristics that have a negligible impact on the motion of dice, then we can develop a way to perform the same result every single time. Like and we define this an initial condition of the throw. So each initial condition would result one situation, like falling on the side or the top or the bottom. So if the process is random and each initial condition has the same probability of occurring, like we say, and then the 3-sided dice will have the same probability of landing on one of its faces and its side. And now let's talk about the reality, and it's not the same as the ideal part, and however the initial condition may not be as random as we think, because we may accidentally influence the selection of the initial condition even though we believe it's random. So if we can try to control initial conditions, making it similar every time, then we can predict that it will tend to have a similar result by falling on the top, the bottom, and the side. And this will then prove that the random isn't ideal and three-sided dice will not exist in the reality. So we believe that three-sided dice is not able to exist in the reality because of the random. So let's talk about the reality. And this is our experiment video, and we released that the dice was facing up and also with a small amount of the height like just this and tilted angle. And we managed to make the dice land on the top or the bottom like the video. And you have them and turn to this side. And now let's talk about the theory about the boundary condition calculation. And here's some physical characteristics that we consider, and so on. There's many physical characteristics in just one initial condition. So we consider about the velocity of dice before dropping into the floor, or the angular momentum of the dice, or the angular velocity of the dice, and the rotation inertia, and the radius of this dice, and the angle between the dice and the floor, like the horizontal part, and we consider many about that. And here's a theory about the boundary condition calculation. And we know that after we put the constant into this formula, we can get one theta, and this is also a constant. So about this constant, theta 0 is as a constant, and if theta is bigger than that, we get the theta 0 and rotate to other side. And when the theta is lower than less than the theta 0, and there were two kinds of phenomenon will happen. The first one is the angle is too big and you won't reach the goal, and the angle is too small enough and you will reach the goal. So here is our experiment by the hands rolling. And first, the theory part is like this. This is the falling on the bottom and the top. They make the plus them together. It have to have about 1500 times, but 0 times to stay on the side. But in our experiment, there are about 600 times on the bottom, and about 700 times on the top, and 250 times on the side. And our theory is that times of the side should be 0. The experimental data doesn't fit our theory, but we can see the trend that we predict. Like here's almost the times that fall on the bottom and the top. Okay, now let's talk about the theory about the existence of the three-sided dice. So the experimental results does fit our modified theoretical trend. However, the chance of landing on this side should be 0. So we believe the error is created by the instability of humans' hand throwing. So it seems to be impossible for human to remain the releasing angle at the right range, but also maintain all the other parameters in the initial condition. So the conclusion is the three-sided dice doesn't exist in the reality because of the initial conditions are not random. So here is our conclusion and claim. The proportional of the diameter to height of the three-sided dice have to be √3 in the ideal situation that we calculated in the geometrical side, and we managed to control the similar initial condition by humans hand throwing, which leads to a trend in our result which doesn't fit the simple geometrical model. So the three-sided dice is not exist in the reality, and this is our experimental result and also our conclusion. Thank you for listening.
Okay.
Okay, here are some questions to ask you. And first, please turn to page 19.
This one.
And I wonder that if there's a mistake to put the edge on the left side and the two times R in the left picture.
You mean this one? And this is the edge, and this is
So it is
correct. This is correct.
So it's a different dice from your theoretical model.
This dice.
So the moment of inertia is of the which axis? The moment of inertia.
Oh, the moment on inertia. This one.
Yes. Which axis?
Just like sorry, is in this one. This axis.
Okay. And for another question is that you release your dice by your hand. So do you think that it will still be random if you release it by your machine?
Yes, it will be random because running by the hand is.
So what if you use a machine to release your dice?
It won't be random if you using the machine, and also you just using the same angles, and I think that won't be random because using of the dice, and like you throw the square dice and you just use your hands to throw it.
So have you controlled the ground? Have you considered the influence of the ground?
You mean the smooth or not smooth?
And the friction or the restitution coefficient?
It may affect, but this is not in our experiment. We also use the smooth floor to do our experiment.
Okay, this is my end of that.
Thank you.
Hello everyone, this is Jason Lee from Joseph Junior High School. And the problem I'm going to host today is problem number 7, three-sided dice. And here's the problem statement. So that a coin on its side is often associated with the idea of a rare occurrence. And what should be the physical and geometrical characteristics of the cylindrical dice that it has, so that it has the same probability to land on its side and one of its faces. And in the next position, we'll mainly focus on can you estimate the optimal cylinder height from this, and for the theoretical consideration, it must be considered on which side the object comes to rest depending on both solid angles when it hits. A simulation that tries out different angles is ideal for this. And here's the structure of the reporters solving the problem. First, they gave us a clear video and the basic motion of the dice, and they move on to the theoretical model, and they consider the ideal probability, and they give us the geometrical model, which is the ratio of the root 3, and they has a 3D printer to make up their cylinder dice and throw 1,600 times, and they use their hands to draw the dice. And for their experimentation, they tried out different ratio of the height and the radius. And for the conclusion, they think that there's no three-sided dice in the real condition because of we cannot draw it randomly. And for the strong and weak points for the reporter, and they first gave us a clear define of the center of mass, and then they use something like the angular velocity, linear velocity, and the moment of inertia to quantify the results. And they also give some experiments to verify the theory regarding rebound, gravity, position, and releasing height. And they also get accuracy of the device, which contains the coefficient of the restitution and rebound. There's also some weak points for the reporter. First, they missed the address of the physical phenomenon, which is the air resistance, and there's no theoretical consideration in the friction coefficient of elasticity, and the torque that is related to the friction and the normal force from the flow. And they also lack of investigation of the deformation, the rotation, and the initial angular velocity of the dice. And also the order of the report is not quite clear. And in the next discussion, where I'm going to talk about what is the area of each side of the dice, and do you think that the area will influence the air resistance of the releasing, and how big is the effect of the air resistance, and how do you draw your dice? Is flipping or rolling, or have you tried some ways, and how is it associated with the results? And is the surface of the dice hard or soft? And how does it affect the experimental results? And will the dice rebound after falling? And will it affect the probability? And also, is the elastic coefficient of each side the same? And how is that associated with the results? And here comes our discussion part. So, do you think that the air resistance will affect the results?
Yes, of course, because it's just like a physical characteristic, so it may affect, but we're going to, because if we can control the parameters, that means we can control the result, right?
Yes, but there's also, because the air resistance is also, in our opponent's view, the air resistance, we think that it is a way to add the randomity. So
What do you mean?
just like when we consider the air resistance, the uncertainty or the randomly, it will increase.
If we throw the dice in the same viscosity and we see the velocity, so the airflow may just keep the same because we throw like the same velocity.
So you think that in real condition, you throw it and it will be influenced by the air resistance, and it will increase the randomity.
Yes, but we're going to control the parameters that we can control the results. So we are going to investigate if there really a three-sided dice in the reality.
Yes, and so how do you release your dice? By just release it, or flip or roll it?
You're going to ask about the first experiment or the second?
Just like the real condition, how do you release your dice?
If is in the second experiment, we're going to throw in the same way. If like this or like this, or we're using the same way, and we're going to try if there is okay to control the parameters and control the result.
So this will affect the. So you think that when we control the rolling or the flipping in the same condition, it will lead to the same results?
Yes, it's in the ideal, but in the reality, we're not able to do this.
Okay. And is the surface of the dice or the soft, and how will it affect the results?
You mean this is the soft?
Just like how hard it is?
It's just like the 3D printer, so
Yes,
it's just like plastic.
okay. And do you think that it will become the restitution of the coefficient of restitution will affect this?
Yes.
So it will also a way to add its randomly.
Yes. Yes, the different kind of material may have different kind of friction coefficient, and this is also a physical characteristic that we can consider about.
So, and also to our core, when the dice rebound, you have observed a rebound, yes.
Yes, it will rebound, and
so the rebound is irregular, or
the rebound is
irregular. So
if we can control the initial conditions, so we believe that if the initial condition is the same and the rebouncing of the dice is the same.
So and from all the above questions, you answer that all of these is random.
Yes, we're going to let it not random because even when we believe we are randomly throwing the dice, and we actually tend to follow a pattern because of the humanity, and even our environment is very similar. For example, the gravity, the temperature, or the humidity, the moisture, and which will all causes the measure of the impact of this.
In real condition, we just throw a dice and not consider anything. Just throw a dice, yes. So it is a way for people throw a dice in randomly because the air, the moisture, anything.
Oh, I understand. And in my first experiment, I throw just like randomly and like this way, and we found the result is not pretty fit our theory. Because of the initial, we have said that the one initial condition may lead to one to falling on the side
So
and bottom.
do you think that the unequal possibility is resulted in your theory or the theoretical error?
Throwing.
Sorry, so, but in our opponent's view, we think because we analyze it with a two-dimensional model.
Yes.
So we think that you can try to use a three-dimensional model to analyze it.
You mean 3D?
Yes.
What do you think is the difference between the 3D and 2D?
So may I use the model? So here is the two-dimensional ice you mentioned. And so the thing that it will form here or here is resulted in the theta.
It's because if this is the geometrically, and we will draw the horizontal line, and this is the perpendicular. So if the center of the gravity is here, and it will go like this.
So it is like how it depends on the theta here.
Yes, in the geometrical, but in the reality, there are many conditions to affect
But in
this.
three-dimensional,
Yes.
you can draw it like this, and and you say that it is √3. So it is like the ratio of this too.
The ratio of the dice.
Just like how much, like when we make a spherical shell on it, and we have a ball, and if there is like or radius 23 to 1
Yes.
in your theoretical model, and it will become, but the area of this would be area of this.
It's
And
smaller than the field one. You mean?
I didn't draw the picture already, so I cannot make sure. But the probability of this and this will definitely not the same when we use a two-dimensional model.
But this is just the theoretical. I believe this is just the theoretical and ideal part of the experiment. But in the reality, we are not able to have this kind of.
Yeah, so what I mean is that when you throw a dice there, the whole motion is all random. So we can consider it as a random condition of releasing the dice.
I think it's not random.
You think it's random?
I want to show out my bigger page about the place demo. So if we so if we know and can control the precise characteristic, then the results can be calculated as predicted. And here's the words that Freud tried the demo.
So do you think that the randomity can be? So you think that if you can control all the parameters that can influence the result, it will
All the same.
It will help us find the totally random dice.
Yes, we mean like we just sorting like this, and again, it would just like this base off.
Yes, that's because your height is not enough for it. And if we use this model, this model, it will touch with the prime maybe or this prime maybe. So when it will rebound too.
Yes,
so if the rebounding height is not enough for the ball to rotate randomly, because the rebound is also random because the structure or the maybe air resistance or moisture is safe, and it will become a random condition for if the height is enough.
Yes, I understand what you mentioned about that. We're going to control the parameters, and you're going to talk about what is random, but I'm going to talk about we want to control the parameters and control the results that is only possible. I only consider edge the random, and when I can make sure the probability of each physical characteristic is I only consider as random when I can make sure the other parameters is always same.
So you cannot store it in a precise way.
Precise way?
Just like you can only store it like in a random.
We can get it in our experiment like this. And so that it's just like rebound, and it will have the same angle to rebound to the right?
So and I think you can also investigate in how to randomly throw the dice, but not control all the parameters. So it will close to a real condition, and maybe this is my end of the discussion.
Yes, I
time is up.
So and here we have a disagreement on how to do the experiment and how we should demonstrate the theoretical model. But we think we both agree on how whatever we cannot control all the parameters into one condition that will get the same result. In theoretical it is true, but in zero condition it is the physical dice is not existing. So maybe just it is not existed, but we may try to do our experiment in a random condition, so we can see if that is a totally random, and to find the correct ratio for evident dice.
Question. Do you both believe that a standard cubicles dice is random? There's a cubicle dice, a cube. Okay, reporter?
No, I don't believe it. Random doesn't exist because of the condition is not always random. Like the ideal is
Okay.
not.
All right. Do you believe that if you drop the cylinder from extremely high, that it would have it would approximate the accuracy of the probabilities?
Well, I think it is when we drop in a really high place, it will become random when it's falling.
Okay, and reporter? You don't have an answer.
Sorry about it. I think in the extremely height end, it will just like changing the height, like the height parameters, and it's just a physical characteristic.
Okay. All right. Moving on to your ideal conditions. Can you, in your ideal conditions, what is the coefficient of restitution with the ground?
Of the ground?
Yes. What is the coefficient?
We don't have. It's not very important because we use the same floor, so the friction will be coefficient. Yes.
Oh, but in your ideal conditions, you derive that the ideal ratio is square root 3, correct?
Yes.
Okay. So.
In the geometrical.
But isn't that assuming that if you have the floor and it lands one way, that it would just stop there and just talk down to either face?
Yes.
So doesn't that mean the coefficient of restitution is 0?
That's why we modify.
That's because so that's why we modified our theory in the non.
Okay. All right. And also about your axis of rotation, right? When you roll it, you only have one axis of rotation, correct?
Now we have three sides, the X, Y, Z. So we have three kinds of rotate.
But when you roll it that way, right? As shown in that image, correct?
This one.
Yes, the one on the
Yes,
left.
because this is geometrical one, so we just consider about this.
Okay. Do you believe the opponent's use of the sphere would work?
Yes, we believe this is this can be
Okay.
considered.
Okay. And to the opponent, do you believe that if you were to throw like the dice all at once, that it would result in the same probabilities if you weren't just to roll it one by one?
You mean in the ideal condition or the
Actually,
condition?
never mind. In your experiment, did you ensure that none of the dice rolled off the table? Because you rolled the dice on the table. Did you ensure none of them fell off?
Yes. Yes.
Okay. Yeah, thank you.
Thank you.
team all nighters, and I'll be reviewing number 7 3-sided dice. To begin, this is the problem statement, and we believe that the main focuses should be how a cylindrical die be rolled to ensure randomness, what relevant parameters affect the landing of a cylindrical die, and how can we use these parameters to find the physical and geometric characteristics of their 3-sided dice. So the reporter's performance, the polls were that they had a diagram and video demonstration, and that they did change the parameter of the ratio of the height to diameter. But the cons were that they drew the dice by hand, which did not ensure randomness, and they also assumed the 2D motion in their ideal model. They also didn't have a qualitative explanation of the phenomenon, no theory for the probability, and didn't really have comparison with their experiments. They also did not show the error in the dice at all. Although they rolled it 1,000 times, they did not show the error, and they lacked the parameters of the material, the mass, and the initial drop. And the opponent, they talked about the air resistance and the flipping process by hand, and the surface rebounding and elastic coefficient. And they asked many questions, which is good. Another poll was that they covered the experimental conditions and factors. However, they did not input their own ideas and had little follow-up. Okay, in the discussion, the opponent asked, have you measured the physical characteristics of the floor? The reporter says no. The reviewer believes that there may exist different 3-sided dice for different types of floor and material combinations. So the physical characteristics of the floor actually do matter in the end. Another topic was, how did you throw the dice? The reporter said we used our hands to throw it randomly. The reviewer says that the method of rolling dice could be impacted by human preferences, so it is not random. And also, the opponent asked, did you consider using a circumscribing sphere to model data? The reporter says no, and the reviewer agrees with the opponent, it would probably be better. Also, the reviewer asked, do you believe that when rolling from high enough, the dice would be random? The reporter said no, and the opponent said yes, but the reviewer believes that it would be. And they also discussed air resistance, velocity, demon, dice throwing demonstration, and the dice escaping. However, they missed a few points. For example, the different axes of rotation, and that could be used, that could be calculated using solid angle and stir radiance. And they also missed the initial potential energy parameter. For example, they did not discuss that if they do throw it from high enough compared to if they threw it really close to off the ground, that it would be much more random, and it would have much higher accuracy because it would be a chaotic system then. They also did not discuss the parameter of the different coefficients of restitution along with the mass and material of the dice, which would cause it to bounce more. And they also did not discuss the friction of the ground, which should create a torque and increase the angular momentum. And also, they all examine like different coefficients of restitution for different ways the dice bounces. Thank you.
Okay, and first of all, I would like to clarify that. First of all, we're going to clarify that we're going to control the parameters. So we're going to prove there's not 3-sided dice in the reality. And here's our concluding remarks. The Q of the opponent is, will hand or machine throwing be random? And the answer of us is that hand throwing will be random, but machine throwing won't. If we can construct a machine that can control all the initial conditions, then the result of every throw will be the same. The second question is if you're throwing random or not. And our answer is we believe that the opponent misunderstood our claim, and that I just claimed yes, precise. And what we're saying is that randomly here doesn't actually exist in the reality because of we can't just change all the parameters. And okay, and another including remarks is how do you throw dice? And our answer is in our first experiment we throw it by randomly, and it's not like actually randomly, but the result doesn't match. So we modify our theory. And in our second experiment we try to throw the same way to prove that initial condition will affect the result. So do you have more parameters that we believe in? Just do. So if we can control all the parameters, so the results may not change. So The next question is, you can consider about 3D, how about 3D? So we agree with the 3D theory, however, we face the same problem in reality when we use 2D theory. So will rebound affect the probability? Our answer is it will, and coefficient is one of kind of physical characteristic that we're going to investigate about.
Now, question from juries.
So, if you consider your ball is not liquid, for example, not 3D printed, very like a cylindrical cake, but when you drop your cake and onto a floor, do you think you can make a 3-size dice?
Okay.
Very deforming.
Cake, I think the cake dropped to the floor and it was broken, and like.
Suppose you are not broken, yeah. You will
Not
be
broken
deformed.
cake?
You will be deformed.
Yeah, that's. I think it's like synthetic dice.
I'm just saying if the size is very informative.
You mean in? I think three-sided dice is not exist. So if we throw a cake, and it may not be a three-sided dice because it's totally not exist in the reality.
So for deformation, we think that if the deformation is big enough, there will be no rebounds for the dice. So it will lead to maybe leads to a accurate theory. It's more closer to the theory than used.
More closer to the theory.
Just because the rebound is one sort of
If it deforms quite a bit, then one thing might be that it would be hard to differentiate between an edge land versus a headland or a tail land. But if it doesn't deform as large, it would be an inelastic collision where it sticks to the ground. So that would be modeled pretty well by this solid angle over there.
Any other questions on how we do this? I have one question, very simple one. Do you think we can control a typical dice, not the dice here, the typical dice that we use in the game? Yes or no, and why? Maybe we start from Hope.
just like a randomity she just mentioned. There's too many. We cannot control it. We cannot control all the parameters to make a really just like a device.
Well, it depends on how you roll it. For example, if you just drop it really close to the table, it will obviously land on one side the whole time. However, if you drop it from extremely high, then no matter your initial conditions, as long as it's high enough, it will still be as really close to 1/6 on all sides, and yeah, it would be random.
As I think there's no random, and if you can control all the initial conditions, and that maybe you can control the side of the typical dice, as same as the three-sided dice if you have the same initial conditions. But I think that may not be able to happen in the reality.
I also think it would be like pseudo-random, which really approximates randomness extremely well. Of course, it's not exactly random, but it's a really good pseudo-randomness.
Yeah, actually, I'm just thinking, is there a way to cheat during the game? So if there's no more question,
An ideal cylinder will have very sharp edge. So do you think the edge, the sharpness of the edge matters?
We think yes, because it will affect it to rebound again because of the sharp edge. So
We think that just like the model, and it will become falling down, like left or right is more clear to where it is false?
We believe that it would impact the coefficient of restitution, which may influence the ideal parameters of the dice.
Okay, I think it's almost time, so. Please. So let's begin from the reporters. So the score for the reporters is 9, 8, 6, 7, 6. And the next is the score for the opponent. 6, 8, 7, 7, 7. And finally, for the reviewers, 6, 8, 8, 8, and 8. Okay, thank you very much for this. We will have a 15 minutes break.